Hey everyone, welcome back. It's your main math teacher, Mr. Boyden, back at it again today, and today we're going to be talking about similar polygons. We're in chapter 7 in our book, so here we go. Let's get to it. Let's talk about a little bit of background knowledge before we get started with a little bit of a do now. Okay, go ahead and read it. Is it a translation, dilation, rotation, or reflection? We're going to rely on what we learned in our previous unit to help us make sense of this unit. So pause for a second and try to answer that question for yourself. Which one is it? Okay, I hope that you can see that this is going to be a dilation. Okay, dilation is the only one of our transformations where the size changes. Okay, the other ones are rigid motions, meaning the size of the shape doesn't change. A dilation changes the shape. 3 turned to 6, 4 turned to 8. So question 2, how much bigger is the big shape than the small shape? That is 2 times as big. Okay, now in our previous unit, do you remember what we called that? We called it a dilation factor. In a minute, we're going to be calling that a similarity ratio. It's the exact same concept, just a little bit of different language, but it's not a new concept, so that's going to be pretty manageable for us. Let's do part 2 of our do now, because we're also going to need this skill today. So we want to solve this little guy right here. Now, I would like to encourage you to take a minute and try this on your own first, and then we can look at it together. So pause the video if you need to, go ahead and solve it. One thing that you should know is that this is called a proportion. And the way we solve it, or the way most teachers teach it anyway, is they use cross multiplication. Okay, and a lot of students usually prefer this method, so that's what I'm going to use in this video. Okay, 3 times 9 is 27, and we're going to cross multiply this way as well, and 5 times x is 5x. Some students forget what to do in the middle here. You need an equal sign, and then we need to just solve. So divide by 5, divide by 5, and we get 27 divided by 5. Now, folks, you can totally leave it that way if you want, or if you prefer, you can type it in a calculator, and you can get 5.4 equals x. Okay, so that's all of the skills that we're going to need in order to access today's learning. So with that said, let's get to it. Okay, let's start with a simple definition of similar that's a little bit easier to think about. So the first way to think about it is when you have two shapes that are the same shape, but they might be different sizes. Now that goes right back to the do now with the dilation. We had those two triangles. They were definitely both right triangles, but they were different sizes. Let's look at a couple of images to see if we have our understanding down. Okay, so first question first. Are these shapes similar or are they not? Let's look at the two lightning bolts. Are they the same shape but different sizes? Sure they are. Yeah, look, they're the same lightning bolt. One's just bigger. So that's a big ol' yes. Okay, what about the next one? These two shapes, are they the same or not? Not really. This one's got all these points or all these triangles around it, so it's something different, so no. What about over here? Are these two the same size and or the same shape? Looks like they're the exact same shape and same size. Looks like maybe it was rotated down, maybe counterclockwise or something like that. So since they're the same shape and the same size, that's yes. Little bonus question for you. If it's same shape and same size, do you remember what that's called? That's when two shapes are congruent. So similarity is just a little bit different. With congruence, they're same shape and same size, but with similarity, they might be different sizes. A couple more examples. Okay, I've got one here with the cars. We've got a toy car, maybe a remote control car, and a bigger version of the same car. Looks like it's a Ferrari, and I would probably want the big one myself, but they're similar. Okay, they're the same exact shape, but they're just different sizes. One of them's a lot bigger. Okay, what about our next one? We got some puppies. This kind of reminds me of me since I got a couple dogs kind of like this. We got a bigger dog and a smaller dog. Are they the same shape? Yeah, they are. Their ears are the same. Their tongues are doing the same thing. Their tails are in the same position. Same shape. One's just bigger. So yes, that's similarity. Here's another example with some giraffes. Same shape, different size. Here we've got a scale model. So that's not actually a hotel. Notice this is just something that's on a table. It's like an architect's rendering. Okay, and this is an application that we sometimes use for similarity. We build a similar model. Why? Because it's cheaper. We want to know how it looks. We want to know what it would look like if someone wanted to walk through the resort, and you can actually get a really good feel for it by doing this. And we do that with bridges and other things that we build as well, because we can cheaply test the situation before we actually spend a bunch of money to build it. We can test the strength of a bridge, for example. Okay. Also, this comes from a paper that one of my IB students is writing, and they actually made a scale model of a racetrack. Now, the racetrack is not 20 meters long. Okay, according to this graph, it looks like the racetrack's 20 meters long. That would be a pretty boring racetrack. It's not very long. I don't think you could even fit a car on it. But what the student did is they made a 1 to 100 scale model. Okay, so this is 1/100th the size. It's a similar track to the one that's the actual real racetrack, but that way the student was able to do the calculations with smaller numbers, so it was a lot easier. Okay, so just some simple examples to help us see what similarity is. Now let's get into a little bit more of a formal definition. This is one that you're going to want to have written down in your notes today. So go ahead and get your pencil and your notebook out and let's start writing. Here's the definition. Two shapes are similar if their angles are, let's try to fill in that together. So we said that they were the exact same shape. So if two shapes were exactly the same shape, would they have the same angles or different angles? They're the same. So two ways we could write this. We could say they are the same. That's the simple way of saying it. Or we could say they are congruent. Okay, and their side lengths are, they're not the same. Remember, they could be different sizes. So we said same shape, different size. So if a different size, it's not that their side lengths are congruent. We want to say that they are proportional. And that's why we started out with solving a proportion today. We're going to see how that applies here in just a minute. So we called it a dilation factor before, but now it's called a similarity ratio. And all it does is it tells us how many times bigger is one shape than another. Now, it doesn't say the word times here. You may want to add the word times to your note. How many times bigger is one shape than another? One more thing on notation before we get into it. This is the symbol that we use for similar. Remember, if it was congruent, it had the equal signs underneath it. Okay, so that was congruent. And it's almost as if when we take those equal signs away, we're no longer saying they're the same size. So not the same size, but yes, the same shape. That's why this symbol means similar. Now for some examples. You may wish to pause the video and draw this one. Okay, which shape is bigger? Okay, that's pretty easy. The bottom shape is bigger. And by how much? And are the triangles similar? So how much bigger is the bottom shape than the top shape? Okay guys, there's a really easy way to do this. All we're going to do is we're going to take that bottom shape and we're going to pick a side length. I'm going to start with 24. Now the question is, what side length in this smaller shape is in the same location? Okay, so pause for a minute, take a look. It is 18, so I'm going to write 18 right there. I'm going to divide that out. I'm going to use my calculator, 24 divided by 18, and what I get when I do that is 1.33. And I'm rounding, but it rounds to 1.33, okay? Now we need to do that for all the sides. So I've already used 24, now I'm going to pick 20, and 20 corresponds to which side in the smaller shape? Okay, be careful. It's actually 15. Sometimes new learners will say 12 when they do this, but notice 20 is on the side that has 2 angle markers and 1 angle marker on it. 2 angle markers, 1 angle marker, so 15 is the number that we need. 20 divided by 15, type it in my calculator real quick. That is also 1.33. Okay, and one more, 16. And now we need to figure out where that corresponds on the other shape. That corresponds to 12. So we're going to bring the 12, 16 divided by 12, that's also 1.33. So let's go back to these questions. And how much bigger is it? Well, check it out, y'all. It's 1.33 times bigger. That answers the question. And we checked all the side lengths, and that relationship holds up for all of them. Question 2, are the triangles similar? Now remember, we needed 2 things for similarity. We needed the angles to match up, and look, they do. 1, 2, 3 angle markers. 1, 2, 3 angle markers. Yes, all the sides are congruent. Or excuse me, the angles are congruent. Then we needed the sides to be proportional. And that means when we compare them with division, we get the same answer. And look, 1.33, 1.33, 1.33. So our answer is yes. Okay, let's look at a different application. Here, we're told the triangles are similar. Okay, that's nice, so we don't have to explain or prove it. And then all we need to do is we need to be able to say, what is x? So check it out. The first thing I'm going to do is I'm going to write down x, and I'm going to figure out where is x on the other shape. Okay, where is that at? Looks like it's at 40. Okay, so I'm going to compare x to 40. Awesome. Now, do y'all know how to divide x by 40? Because I don't, so I'm not going to type that in. My calculator has no idea how to do that. What I'm instead going to do is pick a different number now. So I started with x, now I'm going to pick 12. And 12 is going to get compared to what? 12 is in the same spot as 30. And what I'm going to do is I'm going to make it just like the do now. I'm going to make a proportion. Now before we solve that, let's make one little note on this. Notice those two numbers on the top both came from the smaller shape. And the two numbers on bottom, 40 and 30, both of those came from the bigger shape. Now it doesn't matter if you pick small or big. However, both, when we look at the top, either both of them need to come from the small shape or both of them need to have come from the big shape. Here's where you'd get in trouble. If you instead said x over 40 and you put 30 over 12, that would be wrong. And here's why. Because x comes from the small shape, so you have small compared to big, and then you have bigger number compared to a smaller number. It's not consistent, so that does not work. This will work. Now, if you'd like to pause the video and try to simplify this out, go for it. If not, let's watch. Okay, we're going to cross multiply this way. We're going to go 40 times 12, and we get 480. So I'm going to write that over here. We're going to cross multiply this way. That one's a little easier. I don't need a calculator. And we get 30x. What's our next step? Let's divide the 30 out. So I get 480 divided by 30, and my answer is 16. Now, we should always double check and make sure that makes sense. 16 is a little bigger, and that 16 goes here for x. 16 is a little bigger than 12. Hey, y'all, did you expect x to be bigger than 12 or not? Probably. Looks like it's, we don't know if it's a right triangle, but it looks like maybe it's like a hypotenuse. 40 is bigger than 30, 16 is bigger than 12. Looks like we are in very good shape. Okay, so we solved for x. They also asked, what is the similarity ratio? So all we have to do is pick a side length. I pick 40, and I'm going to divide that by what? Now remember, similarity ratio is comparing two different shapes. So we cannot pick 30 because it's in the same shape as 40. But we could pick 16. And 40 divided by 16 equals 2.5. And some people will ask, but wait, but what if I hadn't picked 40? What if I had picked 30 and I had picked 12? Well, guess what, guys? That's also 2.5. So it doesn't matter which one you pick, but if you pick 30, you need to pick the corresponding side to 30. If you pick 40, you need to pick the corresponding side to 40. So now we've answered the question, and I'm going to label that as SR for similarity ratio. So check similarity ratio, and we found X. We have answered our prompts, and we're moving on. Now that we've had a chance to get an example in the notes, why don't you use that example and attempt this one on your own? So pause the video, draw this one, and give it a try. Okay, here's how it goes. What we want to do in order to find x is I'm going to first start out by writing down what it is I'm looking for. Okay, so for me, that means I'm going to draw my x down here, and I'm going to figure out what's the corresponding number that goes with x, or the corresponding part of the other shape. So x is here, that corresponding part is right over there, so x goes with 2. Then I'm going to put my equal sign. I know there's going to be another fraction, and I'm going to look for a pair of numbers. So what happens sometimes, people start with 3.2, but there's nothing that goes with 3.2, so that's a distractor number. That doesn't do us any good. And then the next thing is, I started with the bigger shape, so I need to start with the bigger shape again. So I'm going to start with 6, and I'm going to pair that up with 5. So 6, 5, let's cross multiply, and I get 12 equals 5x. So let's divide by 5. And then we get 2.4 equals x. We should always pause and double check, make sure that number makes sense. This is 2. Did we expect this x to be bigger than 2? Yeah, probably. It's a bigger shape, a little bit bigger, so 2.4 is probably reasonable, and it's still less than 6, and we can see visually this is less than 6. So we're done. Here's another one. Okay, we're told the triangles are similar. We can see that the triangle on the left is smaller than the triangle on the right, and so it's not a trick question, but this question is sort of trying to trick us a little bit. They're asking for the angle measures. Now remember back from the definition of similarity, what did we know about angle measures? Now you may have to pause and flip back in your notes to find this, but what we had written down was that when two shapes are similar, their angles are congruent. So that means if we know this is 42, which angle is also 42? It looks like the same spot as right here. So that's going to be 42. We know this is 78, so that's going to be 78. And uh-oh, how do we find that? That angle is missing. All we know is that it's the same in both. But if you remember that we know every triangle has 180 degrees, then we could subtract off those other two angles. So subtract off 78, subtract off 42, and let's see what we get. Okay, and when we do that, we get 60. So that means this angle is 60. Let's read the question again, make sure we have responded to it appropriately. They asked us to find the measure of angles A, B, and C. Have we done that? Let's see. A, B, C. Yeah, we put numbers on all three. There's our answers. We're done with this one. All right. Are these parallelograms similar? At first glance, maybe. I mean, this is a 1 and that's a 2, so it looks like it got doubled. This is a 2, that's a 4. Okay, so it got doubled, so the side lengths are proportional. We need to double check and make sure the angles are congruent. Remember, we need both conditions. Congruent angles and proportional side lengths. This has proportional side lengths, but let's see. This is 120 and that's 100. So those don't match up. And if you remember, because we have parallel lines, that the two angles that are adjacent always have to add to 180. That means this is, excuse me, not 180. This is 80. And if this is 120, that would have to be 60. So no, the angles are not congruent. So no, and I'm going to add angles not congruent. Okay, and that's enough reasoning. If you wrote that on a test, I'd give you full points every day of the week. Okay, although let's spell angles right. A-N-G-L-E-S, angles. There we go. Let's look at an application. Pause the video for a second and read it. Make sure you understand before we continue. Okay, we've got a painting here, 24 inches by 36 inches. Sounds to me like it's probably a rectangle. Okay, and this is like an actual painting someone did. Okay, 24 and 36. All right, and we want to put that on a postcard. Hey, that makes sense. You know, you go on a vacation, you send back a postcard to somebody, maybe you went to the beach or something like that, and you want that picture you send back to look right. So we're going to have a postcard. Postcard's probably a little smaller than the original painting. They told us right here that 6 is the length. So what I'm going to do, up here we said 24 was the length, so I got to put them in the same spot. 6 is the length. What is the width? Okay, so remember we had length here. Looks like we had width there, and that means width is down here, so that's going to be my x. Okay, that's what I'm trying to find. And why do we need these to be similar? Well, if you've ever taken a picture and stretched it, like on a computer, you can really warp it badly. And you know what I like to think of is, what if I was in the picture, if I was in the painting? If you made this value of x too big, then the postcard would be too wide. And then I would look really fat on the picture. I'd be stretched. Or if you made it too small, it would make me look really, really, really skinny. Not that that would be horrible, but it would make me look pretty skinny and maybe a little weird. So we want it to be similar, and so what we're going to do is exactly what we've done in previous examples. I want to find x. I'm going to ask myself, what does x get paired with? It's in the same spot as 36. So x over 36. I started here. Remember, my arrows need to go the same direction, so I'm going to make this arrow go to the left too. 6, it corresponds to 24, so I'm going to put 6, and I'm going to put 24. And now it's time to cross multiply. So let's do 6 times 36. And I get 216 when I do that. And 24 times x is 24x. And we will divide the 24 out. And when we do that, we get 9. We should pause and make sure it makes sense. Okay, so we're putting 9 right there. So 24, 36 was bigger. We got a 6 here. 9 is bigger. So that's a good thing. Okay, the pattern holds up. That shows that we have found something proportional. That's a reasonable sounding number for a postcard. So boom, there we go. We're good. All right, here we've got a type of question that now we're probably getting pretty used to. Are the shapes similar? So we're going to check. Are the angles congruent? Okay, this has only 90-degree angles. This also has only 90-degree angles. So we got that part. Are the side lengths proportional? Okay, we need to check that. And there's an easy way to do that. Okay, pick any number you want. Now, the one that my pen lands on first is 20. 20 corresponds to what other number? Okay, it looks like that goes to the same spot on 30. Cool. And then I'm going to pick 36, and I'm going to go to 52. Notice both my arrows are pointing the same direction. I'm going little shape to big shape. So 36 over 52, and then all I need to do is cross multiply these. And then we're going to be able to answer our question. I'm going to write my work over here. Okay, so here I go. 20 times 52. When I do that, I get 1,040. And when I do 36 times 30, I get 1,080. Okay, so what does that mean? I mean, this says 1,040 equals 1,080, and that clearly is not true. They're not the same. So what does that tell us? It tells us the shapes are not similar. So we say no, sides not proportional. And I'm going to put a little arrow because we've shown our work right there. That indicates, or that proves, that the side lengths are not proportional. This one's very similar. Why don't you pause the video and try this one on your own, see if you can get it, and then play and see how you did, and you get some feedback on your work. Okay, same idea as the last one. All the angles match up, so all we need to do is we need to set up a proportion and see if our side lengths are proportional. So 15 over 30, 18 over 25. We're going to do a little bit of cross multiplying. So 15 times 25 is 375. And 30 times 18 is 540. So no, they're not similar. Now, y'all, can you see how these two shapes are not proportional? You see how this one, I mean, they're both rectangles, but this one on the left looks a little more drawn out. Like this one looks visually, it looks like it's a closer approximation to a square. And this one you would definitely call a rectangle, where you may be fooled, if you didn't look at the numbers at least, you may be fooled into thinking this is a square. That's kind of hinting to you that, hey, these aren't similar shapes. I mean, yes, they have congruent angles, but that's a hint that probably not proportional sides, and we've been able to show that here. Okay, again, we're getting close to the end of the lesson now, so this is a really good time for you to pause the video and try these on your own. Okay, so pause if you'd like, and then when you hit play, you can follow along. Okay, I'm going to try to find x first. Okay, and x has to go with 4 because it goes straight across the shape like that. And then what I'm going to choose is 9 and 6. Now, some people get into a little bit of trouble here because they say, but wait, Mr. Boyden, couldn't we do 12 and y? Okay, technically that's true. Yes, 12 and y are corresponding, and if you name them 12 and then y in that order, that would be true. But that creates a problem because then you'd have two different variables in this equation, which means you're not going to be able to get a numeric answer out of it. And so that's not helpful. So be very, very careful. We only want one variable at a time in these. Okay, let's do a little bit of work here. I'm going to get 4 times 9, believe that's 36, equals 6x. Let's divide by 6. And what I get out of that is I get x equals 6. Wonderful. Cool. Okay, let's find y now. Now I'm going to change things up just a little bit. What I like to always do is write the variable I'm solving for first. That guarantees I'll get the information I need. Now y goes to 12. Now people, notice the arrows go in the other way this time. That's okay because I'm doing a different calculation. And you notice I've chosen a different color to indicate that. Each individual calculation, like the calculation to find x, you can only have the arrows going one way. Okay, so now we have to make a decision what numbers we want to choose next. And a lot of people say, oh, 4 and 6, that would be good. I would like to discourage you from that. Now, it's not wrong, but the problem is, let's say that we accidentally made a small mistake in this work up here, and 6 wasn't right. Like maybe the answer was 4 or 7 or 5 or something like that instead. Then we would be using a number that's wrong in our calculation, and that would guarantee a wrong answer. So what I want to do is I want to use numbers here that I know for a fact are correct. And so I know that 6 and 9 are correct. Notice both of my red arrows are going to the right, and so I'm going to use 6 and 9 right here. Okay, now in my cross multiplication, I get 9y equals 72. And we're going to divide out the 9. And then y equals 8. Cool. And if you didn't notice, we have one more to do down here. So I'm going to put my z. Looks like z goes with 15. Okay, we know this 6 and 9 are good, so I'm just going to keep reusing and abusing them. Okay, and there's nothing wrong with that. It's actually the right way to do it because I'm using numbers that I know are accurate to the picture. And so now, little cross multiplying, and looks like I get 9z equals 15 times 6, and 15 times 6 is 90. And that means that z equals 10. All right, let's see. Directions asked us to find x, y, and z. We found x is 6, y is 8, and z is 10. Awesome. One more, and we're out of here. Cool. Try this one on your own. Okay, here's my work. Okay, I get x over 8 equals 5 over 10 for my first setup. And for my second setup, I get y over 6 equals 5 over 10. Okay, and let's solve those out now. Okay, when I do this, I get 10x. So I'm put an arrow. 10x equals, looks like 5 times 8 is 40. And that would mean that x equals 4. Let's double check. 10 is bigger than 8. 5 is bigger than 4. Okay, makes sense. That could probably be 4. That seems okay. And then let's do our calculation for y down here. 5 times 6 is 30. And y times 10 is 10y. And so it looks like when I divide 10 out of there, I get y equals 3. So I got a 3 right there. Looks like the 3 is shorter than the 4, and the 4 is shorter than the 5, which is good because we go smallest, medium, large, smallest, medium, large. That indicates to me that we have probably done it. Hope you enjoyed the video, and we'll see you next time.